Model validation. This video is part of a course on food physics, of which this belongs to the modeling section. This particular video is about model validation. This is the last part of this series on errors, uncertainty, and validation of a model. Please refer to the other videos of this series, like this one, this one, this one, and this one, for the details of errors and uncertainty in building a mechanistic model. So this one is about model validation. As we have discussed in the related videos of this series, models have errors and uncertainties. So let's take a very simple process, in this case canning of a food that has potatoes and ground meat in here, potatoes and ground meat, and we are simply canning or heating this process inside this big vessels, this vessel here, and this is the can. And so this is very simple conduction heating process. So in our modeling we replace this real world process by a heat conduction equation in the cylindrical coordinate with boundary condition and so on. In this process we definitely make some errors. So that's one. Then when we have this equation to try to solve it, we solve it numerically for most of the time, and then in the software implementation of it also we make error because we don't really solve these equations exactly in the analytical sense. So again we make errors. We also have uncertainties due to inherent variability. So here, this one, inherent variability. Let's say in this can, then we have the potatoes, and the potatoes, depending on the source, can vary its property. This is inherent biological variability. There's nothing we can do about it. We can also have inherent lack of knowledge and the uncertainty because of that. So lack of knowledge can be like, it's the material, the meat or the potatoes, do they go through material transformation? We may not know all of it at any given time. So this lack of knowledge also leads to uncertainty in a very real way. So we need to be concerned with reducing these errors and estimating the uncertainties. So the model is an accurate representation of reality. Now, when we press run on a computational software, it often gives us a colorful plot. And because it didn't get stuck, it didn't crash, we kind of tend to think, yeah, we have a solution. But we really don't have a solution. We don't have a solution unless we have validated in some way. Every solution has to be validated before we can really call it a legitimate solution. Because the uncertainties and errors that we discussed in the previous slide are very real. So let's define validation and separate it from a closely related term of verification. Now, the modeling process, let's go over this quickly. So we have reality of interest, mathematical model, and a computer model. And the process goes like this. From the reality, we make simplifications and so on, and we set up a mathematical model that is typically the governing equations and boundary conditions defining the process. And then that model that is implemented in a computer software typically to implement or solve these equations. That's what we call the computer model. And then the output for the computer model, the simulation results, are then supposed to be a representation or a simplified representation of the reality. Looking at it in little more details, we start from reality here and choose a modeling framework with important features based on our current understanding. And so comparing between this reality and whatever approach we choose, there can be two things. So from here to here, we can there are two things. One is uncertainties due to just lack of knowledge, or knowingly we ignore certain aspects to simplify the model. So that is one type of compromise that we are making. And the other one is, are we even including the known variability in the model? So the assessment of this step is going to be called confirmation. And so in confirmation, we are assessing the correctness of the modeling. And this is one of the known terminologies that are used. So here we are simply talking about, did we choose the right framework? What kind of physics did we drop? Did we include the variability in setting up the model, and so on? Now we have the governing equations and boundary conditions here, and when the solutions produced by the computer of these governing equations and boundary conditions here at this step, that is, of course, can introduce errors and so on. And to check how good this is called the verification. So for example, mesh convergence is a way to verify whether the governing equation is being solved correctly. Notice that the verification stage is very different from what we would be talking next, that is validation, because in verification, even if you make this error, the error from the mathematical model to the computer model, even if you make that 0, it still does not have or address reality. So we are still not comparing with the comparing between the computer model's solution and reality is called validation. So that is our most important step. You notice the difference between validation and verification. Verified simply means that the computer is solving the mathematical model correctly, but it's still not being compared with reality. So now in this modeling process, of course, there are errors and there are uncertainties. So we're going to look at those two next. Let's break down error and uncertainty. Okay, so error can be, for example, physical approximation error. That's the difference between a reality and its mathematical representation. Error can also be discretization error, that the mathematical equations, when they're solved numerically, we could be making certain errors. So these are the most important examples of acknowledged errors that we know for sure are happening. There can also be mistakes, which are kind of unacknowledged error. Uncertainty can be due to simply inherent variation. So because food is a biological material, there's going to be the biological variability in the material. And this is given. We just have to see how we can try to estimate this uncertainty. Another source of uncertainty is in the unknown physics. We model based on what we know today. That may or may not be correct. So this potential inaccuracy, that is also a source of uncertainty, philosophically speaking, but we need to be aware of that. So how do this error and uncertainty kind of map on to the validation, verification, confirmation diagram that we saw in the previous slide? So here are the types of errors and uncertainties that can be in a model, and here is the model building process, modeling, software implementation, and then simulation results. And for the processes, there are the three assessment steps in the modeling. One is confirmation, other is verification, and it's finally validation. So let's look at how the errors and uncertainties map onto these stages of modeling and its assessment. So the first big one is the physical approximation error, and that has to do with the difference between reality and the mathematical model of governing equation boundary conditions. So the physical approximation error sits here. But physical approximation can also have unknown physics or potential inaccuracy, leading to uncertainty in the model. So then this would also sit at this stage in the model making. Another type of uncertainty is due to the variability, the inherent variability of the food being a biological material. And that is or need to be included. So this uncertainty will then sit here. It will become part of the model. If the model does not include this uncertainty, then it is a little bit farther from the reality. Back to errors. This time discretization error has to do with how we solve the governing equation boundary condition. The fact that we solve it numerically, we discretize the equations and solve numerically, so we're making this discretization error. So that comes here. This is the one that we try to reduce by doing mesh convergence. Now there are other minor errors like iterative convergence error or some possible error like computer round-off error, but then those are also in the stage of solving the governing equation boundary condition that we have for the model. So those also come here. So checking for these 4, 5, and 6 are called verification. They're not validation. When 4, 5, 6, if they're made 0, even then we have not compared with the reality yet, so we have not validated the model. The validation step here finally compares the results with the real world, which is, and this comparison is typically in terms of comparing with experimental data. Note that this comparison here at the validation stage includes everything, so all of it. I don't want to make the drawing messy, but it includes all of the errors and uncertainties in this stage. That includes acknowledged error and even unacknowledged error, like mistakes, are included in this step. For example, it will include a mistake we made in the units, let's say. Uh, it will include the mesh convergence error. It will include the unknown physics or the known assumptions in the model. Everything is included in the validation stage as we compare between our solution here and reality. This is why it is very powerful. In the following slides, we'll go into details of verification and validation, but the uncertainties are estimated, and these estimates can be considered in the validation stage. A very important point here, this diagram, we have these three stages, and it kind of looks very clean and perhaps a little pretty, but modeling point, the modeling process is iterative. It's not, such clear-cut steps do not define modeling. Here the steps are shown being separate from each other. That's not really the process is. It's kind of a simplified diagram here. It's very important to note that the real process is a lot more iterative. For example, if the reality is not matched by the computer model and its estimated uncertainty, we change the mathematical model. We go back and change the mathematical model, and that changes again the computer model, and that will include additional that will introduce additional steps, and the whole process kind of is iterative. So that it's very important to remember that it is not a one-shot deal, it's an iterative process. Now we will get into few little details of the verification step. We start with simply the use of common sense. As modeling starts, the we get the first set of simulation results. The first thing to use is common sense. Note that it's just a start. It's useful only in early stages. And what kinds of things are we talking about? Are there unusual variations in the plotted variable? If you'd say heating process, then it should go from cold to hot. Suddenly, at one spot, you should not see a higher temperature or sudden changes unless it's explained by the physics. Another one would be, are the values plotted within the range given by boundary and initial conditions? So let's say I start a process at 30 degrees C, and it's just a heating process, and my boundaries are at 100 degrees. So then temperatures everywhere need to be between these two if there is no heat generation or heat uh, taking away by some endothermic reaction, then the temperatures need to be in this range. It doesn't matter the details of the physics or the details of the problem, if we just look at it and see that, oh, temperatures are negative, temperatures are outside 100, then something is wrong. If it is supposed to go from red to blue, why is this sudden color change? So we should never ignore such things, as these are important clues if things are going or not going in the right direction. Believe me, it is possible to have a number outside the range. It's possible. The way numerical solution works, if in early stages or if things are not going well, then it's possible to get such non-physical quantities. Another one to check, for example, is no variation. So you had your initial temperature and you give boundary temperatures, and there's no variation in temperature. Now that could happen because if it's so long time that everything has reached 100 degrees, but typically not. No variation typically means something is not working. Then, are the boundary conditions being satisfied? So if you have an insulated boundary condition, it should not show a temperature gradient, for example. So all these are simply checks for obvious. It does not validate the model. In fact, we are not in validation stage at all. This is verification. Another possible ways to get at verification is by comparing with analytical solutions or other computations. Now, analytical solutions are typically unavailable for most practical situations. And also, if analytical solution is available, why are we even going for the numerical solution? So analytical solution is likely to be unavailable for the exact situation that we're looking for. But what we can do is we can simplify and change the current model kind of slightly, if possible, and or come to a simple version of the model, then we can compare. But this comparison does not guarantee for the more complex situation being modeled. Also, other computations, it is unlikely that someone has done the exact work before us. And if they have, then why are we doing it in the first place? If they haven't, then we can match our conditions by changing the geometry, properties, boundary conditions, everything to that particular computation, to what is used in that particular computation, and then compare with the results of that computation. Again, once this comparison is done, it gives little more confidence, but it's not really a very good use. It's certainly not validation. Okay, so you're sort of building more confidence, but it's not necessarily, it's not at all validating the model. The most formal approach in verification is to do a mesh convergence. In mesh convergence, we refine the mesh until the solution stops changing. This error due to coarse mesh is the most significant error at this stage, and by doing mesh convergence, we try to minimize that error. Now we come to validation, the most important step. So real systems are complex, and it's very hard to capture everything in a model. It's almost never possible to completely capture it Therefore, experiment is a must. It is the most powerful way to validate. We can think of three possibilities: available experimental results for the exact situation, or available experimental results for related situation, or performing own experimentation. Now, one has to be really super lucky that someone did all the experiments and collected data but did not model. Usually, unless the reason for collecting data is for modeling, then the person would have done the model anyway. The data collected are not the exact type that the modeler needs. So this would be really super lucky that if somebody has done all the exact measurements needed. The next best possibility is, and that happens quite often, is there's available experimental data for related situation. So that's what I would call somewhat lucky or lucky. So if there's available experimental results for related situation, then you change the model slightly, hopefully, to the conditions of the experiment so that you can actually compare with those experimental results. Quite often, we have to do our own experimentation. For physics-based models, as we are talking about here, it does not have to be as comprehensive as a study that is 100% experimental. Meaning, for model building, model validation, we're not completely depending on experimental data. We're building a mechanistic model, so we have some physics built into it. So the validation data does not have to be as extensive as if it were a purely experimental study. For most situations, only this comparison with experimental data will validate. And so that is the gold standard. So in our diagram, we are at this stage. This is the validation stage where we're comparing the output from computer model, this one, with all the errors and uncertainties, with actual experimental data that is supposed to portray reality. We'll now make a few comments about this validation and show some examples. A few points in validation are worth considering. How good a comparison is really good enough? So let's think of these two items. For the given situation, what accuracy do we need? Not every problem needs the same level of accuracy. Not every variable, not every computation needs the same level of accuracy. So we need to realize that we cannot resolve all details in a complex problem. We're not trying to do that. We need to be careful about this, that it's good enough. It's for the context, have we resolved the most important physics. So we have to make sure that the primary physics in the context, in the particular application, has been resolved. Okay, so the other point is to note that experimental data can also have significant error. It is not like speed of light, which also has some a small, very, very tiny amount of uncertainty in there, but that's, food data that we collect by experiment is nothing like the speed of light. So is the experiment truly matching the model geometry, material, governing equations, boundary, and initial conditions? This is a very significant one. So even if we design the experiment, we have to make sure that the model is exactly replicating the experimental conditions. Also, the other important part is what is the error in experimental data. So the experimental data should have some estimate of uncertainty in the measurements. And this is very important as we try to compare in a realistic way between the model and experimental results. Here is a validation example of the super lucky kind. This is from my own dissertation. When the dinosaurs used to roam, we are interested in how the temperatures and flow patterns happen inside a cylindrical can like this one, full of liquid that's being heated. The results being shown are not for a thick soup like the one shown here, but for a very thin liquid. In fact, it uses the properties of water. On the right is the experimental work from a, a Dutch dissertation of Hiddink, 1975. Details can be seen in the published research paper below, but it shows the measured velocity profile starting from the can wall this way. So the velocity on the wall, of course, has to be 0 for no slip conditions, and then we have the maximum velocity here, and then in the core the fluid rises because it's heated, so it's lighter, so the buoyant forces make the fluid go up here, and to satisfy the continuity it has to go down in the core. So that's the velocity profile, and that was all nicely measured by this person. So this is like a super lucky situation, and the person happened to not do the detailed model. On the left are the computed velocity profiles from a model that solves the uh, heat equation and Navier-Stokes for the cylinder, and you can see it's a very decent comparison, but as I said, that this is really lucky. Such detailed data of exactly the kind we need as a researcher for the validation is typically unavailable. So here is another validation example where I would say we are lucky but not super lucky, because we are trying to build a drying model, and the experimental data that was available, by the way, details of it can be found in the published work. Experimental data that is available is not for the exact situation that we need, but we could change the model and compare the changed model computed results with the experimental results. By matching the experimental conditions, then we can try to do a good comparison between the model and the experiment. So that is also lucky because those experimental data were already available. But it's not super lucky because it's not exactly for the same situations that we need. And as I said earlier, that just because we validate for the conditions of this experiment, it doesn't necessarily validate for the ultimate situation that we are going to use the model. Most of the time for validation, we are not super lucky, we're not even lucky. So we have to really design our own experiment. So here is an example of designing a custom experiments for measuring spatial temperatures in case of microwave heating. So the first one shows surface temperature using infrared camera as the material, in this case a sphere of a potato um, material or something similar being dried in a microwave oven. So how do we get this data? We make a small hole in the microwave oven and put an infrared camera looking through the hole. That is how we just pick up the surface temperatures. Now note, in microwave drying there's a lot of physics. There's electromagnetics, heat transfer, mass transfer, and including pressure driven flow, and of course the solid mechanics and the shrinkage. So ideally we should validate every physics separately, but this is extremely time consuming and almost never done. So instead we go for the most important ones, and of course the less difficult ones. Most important one can be moisture loss in drying. We also go for the variables that can be measured more easily, like this surface temperature, or maybe a point temperature, or the total moisture, as I already mentioned. So of course this takes significant time and effort, uh, but it still gives us the surface temperature in this case. Now suppose I want internal temperature profile, like spatial information inside, then it is nearly impossible normally. It is a very, very difficult setup. So we were not lucky in this case that I'm about to show, that nobody had done that before, but we were extremely lucky that we could collaborate with an experimentalist. So that is definitely the way to go. Experimentalists have detailed experimental setup, or much of it already done, and expensive instruments and so on. So collaboration is the key. So in this case, we're getting interior temperature using MRI for microwave combination heating. So that's how it looks. So we took a cylinder of a gel that has food properties, and we kind of looked at a section of this gel, and that's what you see here as the measured temperature, and we compare that with our model predicted temperatures. This is an enormously involved and also expensive procedure. But we, as I said, we were lucky that we could collaborate with an experimentalist. In general, it is not feasible to have such very detailed model and also plan on the complete detailed experimentation in the same research group. So in performing our own experiments, like the one on the left, this one, we have to make a compromise. So in this case, we only got the surface temperatures. In validating a model, we should try to compare over as large a parameter range as possible. And I will explain that using this analytical solution for heat conduction for a slab. If you recall, this was for a perfect slab, and it was for constant properties, constant alpha. Okay, So as long as these and other conditions for which the analytical solution was obtained are satisfied, then we can use any value of alpha and we would get a solution. We don't have to worry about small alpha or large alpha. But that is not the case for a numerical solution that is almost always used in modeling of complex processes. So numerical solutions for complex processes generally fail for large parameter change or a large range. So we need to try, as part of validation, try a significant range of the likely parameter and property values because the numerical model may not work when we change parameters or properties quite significantly, even when it has validated for one set of conditions. However, this does not mean we have to make the model work over any parameter value. This is often impossible. Let's go over these concepts of error, uncertainty, and validation with an example in mind. In this case, it is deep frying of a French fry. And what we are after is the transformation from raw potato to this fried state. That's what we are trying to model. So first we think of the potato as a porous medium with heat and mass transfer in it, leading to governing equations like mass balance of liquid phase, gas phase, and all those details we don't want to get in here. But we come up with a set of governing equation and also boundary conditions. Okay, but in this process, from here to here, we make physical approximation error because we're obviously making some approximation. For example, the potato deforms, and we may choose to ignore this deformation. So that's my physical approximation error. The mathematical model, which is the governing equations and boundary conditions here, are typically solved numerically, building a computer model, and this could be commercial code or we write our own code, but the solution is almost always numerically. A numerical solution is not exact, but more importantly, there can be all kinds of issues or things that we need to be concerned about, like is the mesh fine enough? Are the time steps small enough? So all those lead to errors, and the errors that we make here can be checked in different ways. So for example, related to mesh, the errors we check by doing a mesh convergence, or the time steps we check against a finer time step. This kind of checking that we do in this step here is called verification. This is verification and not validation. Running this numerical model produces simulations. Like in this case, we see the moisture profile that shows low moisture on the surface and high inside, as one can expect. So this is now the simulation of the model. In case of frying, two of the things we can compare easily are the measured point temperatures. So if we measure a point temperature, we can compare with that, or overall moisture. Overall moisture, we just look at how the wet changes with time. These two can be easily done. We can also do mechanical property changes, which has been done for the frying problem. This comparison with the measured data is called validation. This is the big one. This is the validation process comparing with the reality. Notice there are many possibilities for validation. Some are difficult, some are easier. So for example, the moisture profile we can predict, but validation of it is going to be very difficult because only MRI can do this kind of a moisture profile validation. Also notice, just because we are validating one particular variable or one particular way, either spatial variation, for example, or time variation, it doesn't validate everything. For example, we can validate the center temperature, but that does not mean we are validating the temperature profile over the entire cross section. Also, for moisture, for example, just because we are validating the overall moisture loss does not mean we are validating the more fine-grained details, like how much is the diffusional transport of moisture or how much is the pressure-driven transport, even though those are predicted by the model. So the point is, all those details are there in the model. We're not able to predict every little detail. Nevertheless, even if we do not validate everything, this process of comparing with experiment is referred to as validation. Note, validation also kind of can address the two types of uncertainty that we discussed. One is due to inherent variability. So let's say these potatoes that we're talking about, there can be variability in there, or the lack of knowledge variability. So depending on the potato variety, for example, the physical properties can change. Such uncertainty can get addressed in the validation stage, where the properties input to the model can be for one type of potato and the experiments are for another type, so things don't match. So then we try to get either the properties for the different type of potato, or run the model, do a sensitivity analysis for a range of potato properties between these two varieties. The lack of knowledge uncertainty about the physics itself, whether the simple porous media model would work, or are there some important material transformation that needs to be taken into account. That also gets kind of addressed in the validation stage, because if there is some material transformation that we did not include in the model, then the experiment and the model is unlikely to match very well. So then we have talked about a few types of error, like these two, this one, and this is called the discretization error. Discretization error. So two types of error, and the uncertainties, and we talked about the validation process in the context of a frying process. So here we summarize assessment of the model or the modeling process in relation to errors and uncertainty. In particular, we would be talking about the validation. So here is my modeling process that we have talked about, and here is the assessment of the modeling process. confirmation and then verification and validation at different stages of the modeling process. For errors, the two primary sources of error are the physical approximation error and discretization error. Physical approximation error happens here, and then the discretization error happens here in doing the computer model from the given governing equations and boundary conditions. Besides, there can also be unacknowledged error, like mistakes, very real. So they all get lumped together and compared with the experiment at this stage, and that is referred to as the validation. Reducing individual errors, like the discretization error here, is definitely critically needed, but it's referred to as that reduction process is more of a verification process and not validation. By making it zero, if we reduce the discretization error to zero, we still have not validated our model. Uncertainty can be due to simply the biological variability, this one here, or it can be due to unknown physics. We don't even know the most complicated or the most detailed version of the physics, so what we are using may not be the most accurate. For uncertainty due to biological variability, this guy here, the model has to deal with it. So the way we do this is by doing sensitivity analysis, and details of that sensitivity analysis has been described in a different video. Typically, once the model is built, then we bring in the biological variability simply by running the model over a range of situations, which can be just range or a distribution of this variability. All these have been discussed in a different video. The next step in modeling is communicating the results, and this is discussed in a follow-up modeling, a follow-up module.